Our next speaker is Werner Magnes. He'll tell us about in-orbit testing.
Yeah, hello. Yeah, I'm going to talk about the scalar magnetometer on this mission. And as you can see, it's a rather large team. So we are leading this activity at the Space Research Institute of the Austrian Academy of Sciences. In Austria, we have the main partner is the Technical University in Graz, responsible for the optics, for the sensor, and also the physics behind this principle. And we have a big partner also in China with NSCC, the National Space Science Center. They built the controller and the power supply unit. They did all the integration and testing in China. And then the Harbin Institute of Technology in Shenzhen, they have the contractual lead and doing the science elements. And with Yi Chang and Keke, of course, we got a lot of support from MUST in this activity. So time, of course, is short. So the right button. Just for topics, I will briefly introduce the instrument itself. Then, what is the main objective of the scalar magnetometer on this mission? Then, how do we verify the accuracy on ground as well as in space? And then a brief summary. The coupled dark state magnetometer. So here you see the flight model. So the main elements, and it is an optical magnetometer. So you see on the bottom left. So the real center part is such a glass cell. But the glass cell in the end, it's not empty. It's filled with rubidium, a special rubidium isotope, and we excite the electrons of this atom to measure the electric field. So we have the cell here in the center, which is on the 4.2 meter long boom, what we just heard, at the tip. And the other center element is here, the laser diode. And the electronics is sitting in the spacecraft itself. And since this is an optical instrument, of course, we have this orange covered here, optical fibers, which guide the light from the electronics to the sensor, to the glass cell, and then back to the electronics. This is the full flight instrument in thermal vacuum test in Beijing. Here you see then also the other hardware that is necessary, of course, to interface to the spacecraft. So there's the controller, all the data processing that is needed on board, and also the power supply and the sensor here and the fibers. During as I said, thermal vacuum test, which was done in Beijing. Just a few words about the principle of this instrument. So I showed you already this glass cell, and this was all invented by my colleague Roland Lammecker of the Technical University in Graz. So we have the rubidium cell, and to the right here we have the absorption curve. So that means how much light of the laser is going through the cell. And based on the Raman detuning, and what is meant here with the Raman detuning, and for that, of course, we have to look into the energy levels of the rubidium atoms, and we build up this kind of lambda system. So we have two energy levels in the ground state, split into the hyperfine structure of the atom, and we have the excited state, and the detuning is this difference here. So in the end, of course, we have a two-photon interference and a quantum interference that's ongoing in the cell with the rubidium atoms. And nicely, when the detuning gets smaller, the absorption gets higher. But when the detuning is zero, then the absorption drops dramatically. And this gives us a very sharp, very tiny feature that allows us to measure the magnetic field, because the ground levels here, they shift with the magnetic field due to the Zeeman effect. And so with that, of course, we can scan very nicely, very precisely the ambient magnetic field. And the reason why we call it a dark state magnetometer is because when we are exactly in this tuning point, then the cell gets dark. So that means there's no stray field, so fluorescence field anymore. And this is why this effect is called dark state effect. What is the main objective of such an instrument? Of course, it should enable the best possible scalar calibration of the vector magnetometer in flight. And so when we speak about this calibration, it was mentioned by Yi Chang already, then we talk about in total 9 parameters. So there are 3 offsets, 3 scale factors, and 3 orthogonality angles, which need to be calibrated and trended in flight. And this is done based on the scalar measurements. And the scalar measurement, as I told you before, it's an atomic instrument. So we say that, of course, the measurement is based on an atomic constant. And so we have a very stable and accurate measurement that we can provide. And so the better the in-flight calibration, of course, the better is the science that can be done with the magnetic field data. This needs a lot of verification work on ground, and especially then also in flight. And here we see the outside of the Geomagnetic Observatory, the Conrad Observatory in Austria, which is a special observatory, which is an underground observatory. And in each observatory, of course, you have an absolute area where you do the absolute measurements of the Earth's magnetic field. And this is where we go to on ground. You see the sensor here mounted on one of the pillars. There are other sensors nearby. And so we can reference, or we compare our measurements with the measurements which are done in the Geomagnetic Observatory. And here we see the sensor mounted. And one special thing that needs to be done is to measure how accurate it is over all angles, because such kind of atomic magnetometers, optical magnetometers, show some heading effect, and this is dependent on a misreading of the Earth's magnetic field based on the angles. And this is what we check on ground, and what we also did for these measurements. And this is the result. Sorry, there are many data points, but just follow the red curve here. Is the heading error with some intrinsic field of the sensor. Unfortunately, there is some remaining magnetic field in the sensor itself, which is a few tenths of a nanotesla, because here we have the full scale is plus minus 0.8 nanotesla. We checked for that, and we know the numbers, and then we correct for that, and the remaining heading error is in these blue curves. So it is below plus minus 0.2 nanotesla. So, and the angle is over this one, when you rotate the sensor by 180 degrees, yeah, this is then the variation you see in the magnetic field reading by the sensor. So that's what we see on ground. And then, of course, well, how do we do that in space? In principle, of course, in space, it's not possible anymore to show how accurate you are actually measuring. And that's the field that we have already measured during the last months. It varies between about 8,300 nanotesla and about 50,000 nanotesla. So we don't cover the poles because the inclination is just 41 degrees. Okay, well, how can we say how accurate is this measurement? And very luckily, yeah, we have the 3 swarm spacecraft also in orbit. And of course, the magnetic field is also measured very accurately by those 3 satellites. And thanks to my colleague at NSSC, so Ping Chubin, sorry. So he did a plot here of the orbits of the 3 swarm spacecraft, so Swarm A, Swarm B, Swarm C. And here, down here, you see the MSS orbits, local time, and the quasi-dipolar latitude. And we have those crossing points here, yeah, where the spacecraft gets really close. And so we compare, the first step is to compare the measurements with the chaos model. And this is plotted here with the color code. So in plus minus 60 nanotesla, we see the difference of the sensors to the model itself. So that's the first step. So we are here on the night side. This is the day side. This is why you see more variation here, because there is the ionosphere currents going on. And now let's jump in those. In the end, of course, we have 6 crossing points. And this is what we see on the next slide, how they overlap. Of course, there's lots of variations. So that means that the root mean square of the distribution that is measured. And here we see data of about 7 to 10 days, I guess. I'm not exactly sure, but it's something between 7 and 10 days of data. While the RMS value is a few nanotesla, we see that the difference in the mean value of the 2 spacecraft is really small. So it is here 0 nanotesla plus 0.6 nanotesla and so on. So in total, it is within plus minus 0.6 nanotesla, which is really surprising. So, and for that, we can show that we measure also the magnetic field quite accurate in space. So this is somehow I'd call it the macro picture of the accuracy. So the accuracy over days, almost over a week. And this is here a plot showing you the micro scenario. Yeah, here we have data just over it's about 1 hour here. And here we see really the details of the CDSN measurements. And I would like to point you to the blue curve down here, which is the optical power in our system. And this is what we struggle a little bit on this mission, that the optical power that goes from the laser to the sensor and back varies quite a lot. in a very short time frame. So it goes up to 35 microwatts here and drops down to 10 microwatts over here within an hour, and we have big changes. And this is a little bit of a problem for this short-term stability of our measurements. And you see that this variation in the optical power gets a little bit into the magnetic field measurement. So the magnetic, here is what we plot here is the CDSM data. So the magnetic fields, the strengths measured by the scalar magnetometer minus the strength of the vector magnetometer, which is already calibrated. And so here is nice to see that there is some kind of correlation. When we have mode changes, then we see some of the jumps and so on. So this is something we are still working on, and just received a message from my colleague that we find better and better tuning almost every day to get rid of this kind effect, so that we in the end also have the full accuracy over the full orbit. In summary, so the scalar magnetometer is operational since end of May, around 140 days in orbit, and more than 2,200 orbits we have seen already. So as shown, the comparison with swarm gives us the impression that the absolute accuracy is within plus minus 0.6 nanotesla. The final instrument tuning is still ongoing, so that we can also have this full accuracy over the entire orbits. And I may finish with the sentence: the CDSM, I guess, is ready for a successful mission. Thank you very much.